Now, so today I would like to tell you a little bit about how we can use magnons for computing, but mainly I will talk about one big challenge which we have to make this dream somehow true is that we need better sources. We need sources for magnons which are more energy efficient and which are more reliable into some sense. And as Burkhard already said, there's a big team behind these different approaches which I would like to shortly present to you. So first, it's my group in Kaiserslautern. I want to highlight especially Moritz Geilen, who did a lot of magnetoacoustic spin wave sources. And then we have cooperations, for sure, with the group of Burkhard and of Matthias Weiler in Kaiserslautern. But for the production of all these systems, you need a lot of nanotechnology expertise. So we are working with IMEC and with IMT in Bucharest. And for everything what is about YIG nanostructures, I work a lot with Andri, and here especially Dr. Xi Wang has done a lot of very nice experiments in the latest time. So this is my outline, a little bit about what we want to do with magnon computing, and then the different type of sources which I discuss. So one is the magnetoelastic source, and I would like to motivate why magnetoelastic is interesting. And another thing is the advanced nonlinear magnon sources, so where nonlinearity in the excitation of the magnon already plays a role. And since I'm sandwiched between two talks which are about probabilistic computing, I also added here our first attempt to create a magnonic p-bit. And maybe that would be very interesting to discuss really with the experts how feasible this is in the future. So very short, what is a magnon? We have the Landau-Lifshitz equation, which is describing our system. And if you solve it, you get the eigenmodes of the system, so the spin waves. So it's simply wave, where you can assign a wave vector to it. And in the dual wave theory, you get also the quasi-particle, which is the magnon, which has some energy and some momentum. And energy and momentum conservation play a big role in describing magnon processes. So what is magnonics? Magnonics simply uses magnons or spin waves to process data. So this is our idea. And if you think about how you go from the conventional, I would say, electron-based systems, so you have an electric current, which is a scalar variable, and it's driven by a potential gradient. So now, if you go to magnonics, there's a big transition in computing paradigms. So if you go to, in general, to wave-based propagation, you have a vector which has a lot of different ways to encode information. So you have the amplitude, the frequency, the phase, or even the wave vector. And the whole thing is now driven by wave propagation. So that in our systems, there is no gradient of a potential which drives magnons, but you excite locally and then study simply the interference. So the interference effects is the most important effect for our logic. With this, you can create simple logic gates like NAND gates, or more advanced systems like majority gates, for example. But if you add then the intrinsic nonlinearity of the magnons, you can get to more advanced functionalities like adders or different multipliers. And the good thing is we are scalable into the nanometer wavelengths at gigahertz frequency. So I think the record at the moment in YIG is about 30 nanometer wavelengths, which you can coherently excite, so where you really can process information in the amplitude, frequency, and phase. And for sure, we also want to use frequency multiplexing. So there is a very nice review about magnon computing or spin wave computing here. And you see there are a lot of different topics which are under discussion, which I do not want to address all today, because then I would really have no time to present our work. So I just would like to pick from this big point here two systems which we are interested in. So it was for a long time always binary computing. So for example, we have created this magnonic half adder, which is simply based on nonlinear interference of spin waves. So you simply look on waves which are interfering, and based on their nonlinearity, they change their wavelengths, they change their coupling in these coupled systems. So this is the so-called directional coupler, and with that you do your logic. And that can be quite interesting, because only some of these wires can replace 25 transistors, for example. And on the other hand, we are at the moment heavily studying neuromorphic networks based on spin waves. For example, to use spin waves to connect different spin orbit torque or spin transfer torque autooscillators. So to use principally spin wave multiplexing to have this high integration density with a low number of physical connections here, these waveguides. So it's a little bit similar to the talk we have heard this morning, just that we try to stay in the spintronic domain and try not to go to the RF in between. And why do we try to stay in the spintronic domain? So for spin waves, usually we do not have magnetoresistive effects to read out. And that's a big problem because the energy efficiency, if you look on the circuit principally, from the input, from the CMOS into the spin wave domain and the output, this is what consumes the energy. The energy in the magnonic domain is usually something like attojoule per bit, so you can completely forget it. But since we are using, at the moment, inductive techniques to couple the data in and out, the conversion from the electric domain to the magnonic domain is our bottleneck for any application. So you can do two things. You can try to move or to reduce this process to make all computation as much as you can inside the magnonic domain, or you can improve the conversion efficiency. So make this process better. So you could use spin orbit torques or VCMA, voltage controlled anisotropy. Today I will talk about magnetoelectric and elastic coupling, and in the end also a little bit about novel nonlinear effects, which are still driven by inductive techniques, but which have also some advantages. So let's come to our first source. It's the magnetoelastic magnon source. So why do we want to have this magnetoelastic source? Here it's a benchmark from the magnonic half adder and its power consumption. And you see, in general, the adder itself has a quite good benchmarking against CMOS, but the problem is you need to amplify the signals after each step, or you need to read them out after each step. And then you see if you use electric current-based techniques, you have 10 to the 5 attojoules per operation. So this is much too high to have anything in competition with CMOS. But if you use a voltage control systems, then you can go to attojoule energies. And okay, I think in spintronics, this is the general trend for manipulation of magnetism with very low energies. It's voltage control is the way to go. So we want to use voltages, we don't want to use currents. And then a possibility to go is to use direct electric magnetic coupling. So for example, to use a multiferroic system where the electric degrees of freedom and the magnetic degrees of freedom are directly coupled. But the problem is there, the choice of the system is still limited. So there are not so many materials which are multiferroic and have a low magnon damping and fulfill all the other requirements which we have for magnon computing. That's why we have chosen here a detour principally. If we go from the electric domain via piezoelectricity in the mechanical domain, and then via magnetoelasticity into the magnetic domain. So principally what I will show you, we have a phonon to magnon converter, we have our microwave, we use the interdigital transducer, which you all have in your smartphone, to transduce the microwave signal into a surface acoustic wave via piezoelectricity. So we create phonons in the end, and then we get magnons. And I principally want to show you that there is more than just creating from one phonon one magnon, but that we can use these phonons also to amplify magnons in very interesting ways. So our description is here in the micromagnetic framework. We use the magnetoelastic field. So we have some magnetoelastic energy density, which depends on the strain S, and the magnetization components, and from that you derive the effective magnetoelastic field here, which you can compose of the normal strain component and the shear strain component. So that looks very complex, and in fact it is, because now this field here itself depends on the orientation of the magnetization. So it's much more involved than simply using the field of an antenna. So how do we detect our magnons and phonons? The good thing is we use Brilliant light scattering, spectroscopy, microfocused systems here. And the good thing is simply that it's possible with BLS to detect phonons and magnons simultaneously. And another good thing is when we analyze the polarization of the backscattered light, we can even distinguish if we have a magnon or a phonon. So you see principally here the phonons in red, they don't turn the polarization of the backscattered light, whereas the magnons, they turn it. So we have a way simply to see phonon signals and magnon signals at the same frequency and look principally how the system is translating phonons into magnons. So this was our first try, simply study how we get linear excitation of spin waves. So how is a phonon translated into a magnon by magnetoelastic coupling? So we excite our phonons. We have here our cobalt iron boron magnonic microstructure, and then we let simply the surface acoustic wave propagate here, and via the magnetoelastic field, which is produced by the surface acoustic wave, we create our magnon. And we have a special geometry to optimize this coupling. So if you are working in magnetization parallel here to the phonon propagation or perpendicular, there is no linear interaction, at least with the main component of the surface acoustic wave. So you need to have this 45-degree adjustment. And then if you change the magnetic field and see which magnons are excited by the phonons which you apply to your sample, you nicely see that there's this phonon-magnon resonance. And if you probe that as a function of the excitation frequency and compare it to the dispersion relation, you nicely see that the trivial resonance condition is fulfilled. So the K vector and the frequency of the quasi-particles are conserved. So momentum and energy in this process are simply conserved. So if we go now a little bit more into the depths of the physics and want to study also nonlinear phenomena, which are very important for amplification of magnons, we can, for example, use some Hamilton formalism for this nonlinear hybrid system. So principally, we have our Hamiltonian, which includes spin wave amplitude operators and phonon amplitudes, and then here up to the second H2, we have the harmonic oscillator. So this is all linear excitation and linear spin waves. And then we have the 3-magnon process, the 4-magnon processes, and also magnon-phonon processes. And as an example, I have plotted here, for example, 3-magnon scattering or splitting, where one magnon splits into other magnons, or on that side, the acoustic magnon pumping, where one phonon splits into magnons. And in the end, this process is what we want to use, because you can already see you create magnons and you can create them even at different frequencies. So, and from all these processes, you can create so-called magnon instabilities as soon as the energy flow provided by these secondary magnons overcompensates the damping of the particular magnon mode. You will see an exponential rise of the intensity in the system. So how do these magnon instabilities behave? So we have 4-magnon scattering, which I don't show you today, but what I want to show you is the 3-magnon scattering. So you go to an external field where there is no direct linear excitation of magnons by the phonons possible, and then you increase the power here more and more, and suddenly you see the appearance of many different additional magnon modes. And that really confirms that you have this nonlinear process. From the energy analysis of these 2 modes here, F1 and F2, you see that the energy conservation is fulfilled. So principally, one phonon here at F0 decays in 2 magnon, one at F2, one at F1. And from the micromagnetic simulations, we also see that the wave vector conservation in this system is fulfilled. So the phonon is carrying a significant wave vector here, K0, which then leads to 2 different wave vectors also matching principally these 2 frequencies in the isofrequency curves. So this picture is principally the easiest to understand, that we have this quasi-particle scattering process, which is a threshold process because you need to overcome the damping of these 2 individual modes. So how can you use that in the end to do something useful? Okay, sorry, I forgot, I also need to discuss a little bit about the underlying physics. So principally, we would like to have this acoustic pumping process where the phonon decays into different magnons. And from our theory analysis provided by Roman Werber from Kiev, we found that this indeed is the dominant mechanism in our system, but it's influenced by an additional 3-magnon instability, where first the surface acoustic wave is translated into a non-resonant magnon excitation. So you are very far from a resonant excitation. It's a forced oscillation, which then decays into these 2 magnons, and which changes principally the critical or the distribution of your result in wave vector space. So this analysis is somehow important to predict correctly at which wavelengths and at which frequency your magnon modes will appear if you drive the system into the nonlinear instability. So, but the important thing, the acoustic pumping is the dominant process, because you can make this effect even more efficient. So you can go into geometry where the external field is aligned along the phonon propagation direction. And in this case, there is absolutely no linear interaction with the main component of the strain of the phonon. So in the linear case, you will create nothing. But in the nonlinear case, you interact with already existing thermal magnons, and these magnons can then be amplified. So this is a micromagnetic simulation which shows you where you are then in wave vector space and frequency. And with this, you can create some amplifier for magnons. So principally, if you send in one frequency f1 and in addition the surface acoustic wave at the SAW frequency here, what you get out is a strong signal at f2. So you change the frequency of your system. So it's a frequency converter and an amplifier in addition. So you have a completely novel way to work in your magnonic systems, for example, also to use multiplexing, because principally you can send one frequency in and get another frequency out, and the frequency difference is simply adjustable by the frequency of your surface acoustic wave. So at the moment, we are realizing the system also, this special kind of frequency converter on the microscale. And with this, I would like to show you only shortly the scaled approach. So principally, IMAG has developed this magnetoelastic electric cell where everything is embedded into one single nanostructure. So you have the they have the piezoelectric material and the magnetostrictive material in a nanoscale system. And principally, here you see the production process and what we have measured as a phonon spectrum. So if you have an 80 by 80 nanometer pillar, it's possible to emit phonons coherently from that pillar. And principally, we also fabricated larger ones. So, but what is important to show principally is that these nanopillars really emit coherent spin waves. And to prove that, principally, you can again test the different geometries. So you can apply the field here. This is our waveguide. This is this magnetoelastic cell, which is producing strain mainly in this direction. So you can apply the field in different angles and check the result. And if it would be simply an inductive excitation, these 2 geometries, the Derman-Eschbach and the backward volume, so 0 and 90 degrees, they would be also very efficient. But in fact, with the magnetoelastic excitation, you see only under 45 degrees between these 2, you get an efficient excitation, which really proves that there is not a leakage current which really runs our system and creates our spin waves. So this is principally the proof of the magnetoelastic magnon excitation in the scaled device. And with this, I would like to come to this advanced nonlinear magnon source. So what we use here is a yttrium iron garnet nanostructure and a very traditional way to excite the spin waves with some microwave current in some very large antenna. And the good thing about the large inductive antenna is it has a low ohmic loss. Yeah? Only 5 minutes. Yeah, so I will be fast. And but we have a low excitation efficiency for short waves using the linear process. And what we then could observe is principally in these systems, we have a giant nonlinear frequency shift of about 30% of the total frequency. And we have a large bistability window where we can create high magnon amplitudes or low magnon amplitudes simply depending on the history of the system. So you have hysteresis in magnon amplitudes. And so principally, the nice thing is since we shift a lot the dispersion relation in this system, we have locally a drastic nonlinear shift. So we excite principally a k vector of 0, and then this translates into very short waves here, which are emitted from a very large antenna. So it's a nice way to create short waves, even with large structures, simply by using this nonlinearity. But what is more important, since it's a nonlinear effect where you principally drive your driving or your ferromagnetic resonance to your driving frequency, it ends up in being independent of the driving power for up to 2 orders of magnitude. What you get out is spin wave intensity. So principally, you can vary the microwave power here from almost 0.1 to 10 milliwatt in this case, and your spin wave intensity will not change. So this is very important for novel spin wave or frequency sources, because with this you don't need to care anymore about how to adjust the microwave power at your device. It just depends on the frequency and the magnetic field, what amplitude you will get out. And with this, I would like shortly to come to the magnonic p-bit, because what we discovered is that we can switch between these high power and low power magnonic state if we use trigger pulses. So we apply a very high frequency in this bistability window, and then we add some riding pulses of only 50 nanoseconds. And if we combine these two pulses, then we see that the right pulse is triggering the transition from here to there for this high frequency, and that simply the energy or the information is stored in the system. So we have some kind of volatile magnon memory, and this is actually absolute analog to the concepts which you have for all optical RAMs or for photonic memories. And since this process turned out to be statistic, we started to think about magnon p-bits. So this is just the way we measure it. It's we can skip that. It's simply extending the measurement time to be able to probe a single and individual magnon event instead of averaging over millions of them. And with that, we found that we have a stochastic window for this triggering power. So principally, switching between the high power and the low power state is stochastic, where the probability can be adjusted by the trigger power. So principally, you have a p-bit where you can control the fluctuation or the switching probability simply by the external applied power. And based on that, you can principally create, for example, a magnonic multiplier based on 2 magnonic p-bits, because when we use here 2 probabilistic magnon sources which fire pulses with a certain probability, then you can use the same effect in the clever combination of the interfering magnons to create a magnon AND gate, and with that you simply have realized a magnonic multiplier, which is based on the traditional, I would say, a binary multiplication in probability-based computing. And with this, I come to my conclusion. So I've shown you that we can create magnons using nonlinear processes involving phonons. So we have a new way to electrically excite magnons via the phononic detour principally. Based on this effect, we can create novel types of nanoscaled magnon sources, which, what I didn't show you, even have ferroelectric properties. So you can also use ferroelectric hysteresis to reconfigure the systems. And in the end, I've shown you that we have done principally the first step to a magnonic p-bit. So thank you for your attention.
Thank you very much, Philipp. And